I sure hope I make some money for this because baby needs a new pair of shoes. Okay, so angular momentum. Angular momentum. Wow. This is really fabulous. We've got angular momentum, and we're going to look at our linear momentum first. We know it. We know what linear momentum is, right? Easy. P equals mass times velocity. Rotational momentum, also known as rotational, aka, is called L. All right. So L is the word, and it's going to be our I and omega. So these are the same counterparts, right? I is the counterpart to m, mass. It's our moment of inertia. And omega is the counterpart to v, velocity. Our omega is our angular velocity. So makes sense, right? So what are the units of L? The units are going to be kilograms meters squared per second. Of course, the radians, the ghost of radians disappeared. GHOST of radians disappeared. PEARED. So the ghost of radians is gone, and we're dealing with L, which is our angular momentum. Love it. So now we've learned two things. We've got our I, a new thing, which is our moment of inertia. We've got our angular momentum, L, and we've got our omega. All right, so here's what I was trying to do earlier a little bit. I was trying to talk about the Earth going around in a circle. Oh, that didn't work. Let's try this again. Let's see if I can get down the middle of this thing. Okay, yeah, almost. Okay, so we've got some omega. There's about 1 hour where I actually hold it together. Okay, so omega, going around in a circle. Here you and I are right here in Colorado, and we're going around the world slowly. What is our angular momentum for the Earth? So let's figure that out. First, we need to know what the moment of inertia is for a sphere. Did I say that right? Moment of inertia? Yeah. So we want the moment of inertia for a sphere. So you go to that figure 1011, I believe it was. So we're going to go to that and notice that for a sphere spinning on an axis right down the middle, it's 2/5 the mass of the object times its radius squared. Okay? So that's one thing. And then we can put that in. So we're going to put in 2/5 the mass of the Earth, the radius of the Earth squared. And then we still have to figure out what omega for the Earth is. And yeah, so I don't know if you guys remembered. I don't want to refer back to it, but there was on the test, we figured out what omega for the Earth is. But we know that in one day, we do one revolution. 1 revolution is 2 pi radians. So 1 revolution per 1 day. I'll put a 1 there. So we need to multiply that. What's 2 pi radians? Is 1 revolution. I'll put rad here. So that'll get rid of our revolutions. We're going to multiply by 1 day is 24 hours. This is going to take us a while. So 1 day is 24 hours. We're going to multiply that by 1 hour is, I'm going to jump to 3,600 seconds. I hope you guys don't mind. Because I could have said 86,400, I guess, would have worked. But I didn't do it. So we can get rid of the hours, we can get rid of the days, and we can get rid of the revolutions. And we're left with radians per second. And what is that? That's 7.27 times 10 to the minus 5 radians per second. So, we don't know a couple of things. What else don't we know? The radius of the Earth. We got to have that given to us, right? So the radius of the Earth is 6.4 roughly times 10 to the 6 meters. And the mass of the Earth, fairly large at 6.0, weighing in at 6 times 10 to the 24 kilograms, the Earth. And the Earth, I swear I haven't been drinking. Good. So we know everything, all right? And all we have to do is insert into our equation these things. So we're going to get the angular momentum of the Earth, 2/5. Everybody knows that's 0.4. So we're going to plug in 0.4. You could just multiply everything by 2 and then divide everything by 5. That's fine. You could do that. I'm going to do this. And 6.0 times 10 to the 24. And I'm leaving all the units to the end because what I'm going to do is just slap this on the end. I already know I've got everything the way I need it, so I'm just going to put that on the end and not worry about units. Okay, so I've got my mass of the Earth. Now I need my radius. All right, so we're going to multiply by 6.4 times 10 to the 6 meters. But our radius has to be squared, so we're going to do that. And then we're going to multiply by 7.25 times 10 to the minus 5. And all of those things are going to go into the calculator, and it's going to come out as 7 times 10 to the 33 kilogram meters squared per second. So hopefully that's what you got when you did it. Because I know you did. I just know it. I know you pushed pause and you were like, I can do this. And you could. Okay. Should we go back up? Believe it or not, I've been holding it all together. So should we go back up and do our linear momentum, angular momentum thing? Let's do it. We're going to go back up to our big list of all the things that we put together. Normally I write this on one board and then go back and forth on the other boards, but not today. Not today, boys. All right, so our angular momentum is equal to I omega. And over here, our linear momentum, P, is equal to our mass times our velocity. Cool. Now I'm gonna do a little trick. Oh, I had a spot laid out for it. But let's leave the delta P times Ft there. That's our impulse. So impulse. And we're going to do this. We can do the same thing. We can say delta L is equal to our torque times time. Okay, so our rotational impulse is also an impulse, same. Okay, do we have any more of these? I don't think so. But so we've got this momentum analog, and we've now added this impulse analog. We've done a lot, guys. You've come a long way, Virginia Slim. So let's go down here and get back to, I don't think I have any more relationships to add, so that's nice. Okay, so we're gonna do a lazy Susan. I don't know why they think Susan's so lazy, just because she won't get up out of her seat and grab some food, spinning this thing around on the table. Here's our lazy Susan in the middle of the table. And of course there's ketchup on one side, and it's not where I want to be, where I want it. So I have to spin it around, and there's a radius, and I'm going to apply a force totally tangential so that the cosine, the torque, has no sign to it, right? Because it's perpendicular. And totally perpendicular. We're going to apply that force for a certain amount of time. Okay, so our time, let's lay it out. Our time is 0.15 seconds. This is an example, the lazy Susan example. I don't know, maybe it's in the book, maybe it isn't. You never know. I sometimes make stuff up. So, hard to say. All right, so let's say our time is 0.15 seconds. Our force of the person is very light. Doesn't have to be a lot. They stick them on ball bearings so they'll glide. And then we've got some radius of 0.26 meters. Not 26 meters. That would be a cool lazy Susan. You could put a lot of condiments on that thing. So here's the question. A, what is the final angular momentum? I'm going to call it Ang Mom. I hope you guys don't mind. What is the final angular momentum? We're going to just say LF, okay? If it starts from rest, omega equals 0 radians per second. Okay, so you can pause, see if you can figure it out. now that you're now that you're back, we can do this thing that I like to say. Do we want to use this equation? Well, I mean, fine, but we don't know a lot, right? We don't know a lot of stuff, so no. We don't know the moment of inertia. We don't know what its final omega is. We don't know all kinds of stuff. So that's a big no. But what could we use? We can use the thing I just showed you, where the torque, of course it's the net torque, is equal to our delta L over time. So our angular impulse divided by the time is going to be our torque. And what's our torque? Our torque is our force times our radius. Times the angle between them, sine of the angle between them, but that angle is 90 degrees, so we're going to multiply by 1, so we don't have to worry about it. And let's move. I'm really sorry I'm coughing. I'm not dying, I swear. Not till later. So, delta L. What is delta L? Delta L is equal to our LF minus our L initial. Okay, we can use this for L initial. Why? Because omega initial is 0. So that's going to scratch this guy into a 0 situation. So nice, we're happy with that. Now we can say delta L is essentially LF, and LF divided by T is equal to the radius times our force of the person. Solving for LF, we can get LF is equal to RTFP. Oh, what do you know? We know all those things. RT and FP. Nice, good for us. And we can put those things into our equation. LF is equal to 0.26 times 0.15 times 2.5 newtons. I just got some new glasses. I won't be wearing them to school because I just found out, they bought them for me. I just found out they're really, really shiny pink, like a metallic pink, and they make fun of me. I didn't know it here at the house. And because I'm colorblind and I thought they were gold. So, yeah. Crazy. Good. So, what is that number? That is 9.75 times 10 to the minus 2 kilogram meter squared per second. That's our LF. So I'm gonna sum it up. All right, that's our answer. Because we used this equation. All right, not this equation. We're gonna Ghostbusters that thing. Okay. B. We got more to this, of course. Now we know. Oh, now you tell me. We just learned, breaking off the presses, the mass of the Lazy Susan is 4 kilograms. It's a heavy Lazy Susan. You don't want to try and lift it up. You can put it on the table and the babies won't push it around because it's too heavy. Okay, so that's the mass of the Lazy Susan. The moment of inertia of the Lazy Susan is it's the same as a disk, right? So we're going to say the moment of inertia of the Lazy Susan is 1/2, because we're going to go to that one place, look it up, and we're going to see that it's the mass of the Lazy Susan times the radius of the Lazy Susan squared. So that's our I moment of inertia. So we kind of know these two things now, and so we can generate a question, and that is, what is omega final? Okay, go ahead and pause. Figure out what omega final is. I know none of you guys are pausing. That's fine. Whatever. But pause it. Okay, so we're back. I hate it when they go, okay, pause, and then they wait like a minute. What? Why wait? You paused it. You don't have to wait the minute. So we know we can now use this, okay, and easily solve for omega final. And that's going to be our LF divided by our moment of inertia. For the disk, so the hard part, what's the hard part here? Hopefully you guys found the hard part was figuring out what I was. So it's our 1/2 mr squared. Plugging those numbers in, you get 0.135 kilogram meter squared. If you don't get that, I don't know what to say. I might be wrong. I didn't write any of the numbers out, so. Fine. Now we can plug those things in. So we've got our I here, and we've got our LF there. I'm gonna do the units this time. I don't normally do the units, but we're gonna knock it out and make sure we have the right units. So LF, let's put it in, 9.75 times 10 to the minus 2. I'm gonna put kilogram meters squared per second over there, and we're gonna be dividing by our 0.135. You know what? I'm not going to write it like that. I'm not going to write it like that. I'm going to write it like 1.35 times 10 to the minus 1. And it's kilogram meters squared. All right? So denominator and a numerator is a denominator. And that and that are going to cancel. So I'm left with my radian. Ghost of radians pops back into the scene, and we have radians per second. So there's our unit analysis. Let's handle the numbers. I'll do this. This is how I do it at home, okay? So 9.75, I'm entering that in. I'm going to do 1.35, divide. And I have 7.22. All right, now the only thing I don't know is times 10 to the what, okay? So 7.22 times 10 to the what? Well, 10 to the minus 1 in the bottom is like 10 to the 1. So I've got minus 2 plus 1 leaves me with minus 1. So 10 to the minus 1 radian per second. Hope you followed that. That's how you do it. That is how you do it. So that's our answer for B. Good. Nice work. Congratulations, everyone. Now, conservation of angular momentum. is a thing. It's another conservation rule. Oh, not only is my handwriting bad, I'm slow. So, at least it feels like I am to me. You guys are probably like, oh God, how slow could this be? Oh, jeez. Well, take that time and try and suck up some other of the information that's already out there, written. Okay, let's deal straight with the impulse. Okay, because this is our topic. So let's deal with the impulse rotationally. All right, so what is that? That's delta L, and that's equal to my torque net times the time. We can say delta T or T, whatever. So our torque net is equal to delta L over delta T. Typically T0, initial T is 0, so our final T is the only one we care about there, and we've got L final minus L initial up on top, and then T, just some time. Now, if we are conserving angular momentum, so that means that L final equals L initial, our torque net then has to be 0, right? Because we're looking at this final thing and it's equal to the initial thing. That gives us a 0. There's no way around it. So delta L equals 0. Just like the momentum situation. If you don't have any forces acting, then you're going to maintain momentum, okay? So same thing. If you throw a torque on there, your conservation of angular momentum disappears, all right? So this only occurs when torque net equals 0. Okay? So this is huge. That will give us our conservation of angular momentum. Okay, where are we at? Oh boy. What do I need to do? Set timer for 20 minutes. If I don't have this done in 20 minutes, all right, I'll give myself 30 minutes because, yeah. We're going to apply conservation, all right, of angular momentum. Before I do, I want to do one thing. So, and it may take us 30 minutes. So, before I do, I want to do one thing. Here's a hammer. Okay, imagine, I don't know, who is it? Thor? Thor's got Mjolnir. It's a pretty sweet hammer. It's the best, actually. And I'm not going to tell you the game that it's in. It's the best, but it's awesome. So we've got this hammer, all right? What do we have in this hammer? We've got two things. We've got a stick, and then we've got some metal, big old metal mass, right? That you don't want to get hit with. By Thor, of course. So we've got this metal mass and the stick, and fabulous, good for us. What is the moment of inertia for this thing? Well, you can say for the whole hammer, that's really the moment of inertia. Okay, of course, it's spinning around this pivot point down at the end. All right, so it's going to be the moment of inertia for the stick plus the moment of inertia for the metal mass. Now this is where all the weight is, right? But we can consider the metal mass as a center of mass, all right? And we can end up adding these things together to get our total. So we can get the I of the hammer, the moment of inertia for the hammer. So what do? We find the moment of inertia of a stick, and do I have that written down anywhere here? I can never remember. I think it's 1/2 mass of the stick times the length of the stick squared. I better make sure of that. I don't want to take us down the wrong. I don't want to take us down the wrong road. Pretty sure that's right. It's for a disc. Same for a disc. Where's the stick? Didn't I do a rod, a long rod? I swear I did. See, I don't memorize these things. I just want you to know. I do not memorize them. Oh, I'm so glad I looked. It looks like it's 1/3 ml squared. And I'm pretty sure Nick knew that. Nick is catching me. Okay, so 1/3 ml squared for the stick, all right? And then we got to add in the mass of the hammer. But the mass of the hammer is the easy one, right? And because it's some distance r away, so we've got the pivot point there, the center of mass there, so it's some distance r away, and we're just working with that center of mass. We don't care about the rest of it. We're just going to worry about the center of mass. So we've got our mass of the metal mass and the distance r squared. That's it, just like the dumbbell before, okay? We've added in our stick, and so we can say, oh, great. This is our moment of inertia for this situation, okay? I'm laying that out first because what's going to happen, did I lose my page? What's going to happen? We're going to have a couple of things because we're going to do example 10.15. Okay, it looks like it's straight out of the book, so you can follow along with me, go back through it, look at the book, and make sure you're understanding what's happening. So we've got two positions. We've got a before and we've got an after, okay? And I'm going to, let's do that. We're going to start fresh. Okay, on a table. Here's our table. There's a stick that's going to spin around in a circle, okay? I always draw my circles from in a counterclockwise fashion, but the stick is actually going to go in a clockwise fashion. Okay, so here's the center where it's going to pivot, and I'll erase the circle. And I've got a brick that is coming in. Is it a brick? I don't know. I definitely know I have a stick. So the length of the stick is equal to, length stick is equal to 1.2 meters. Stick is very thin, okay? So we can think of it as a thin rod. The mass of the box that's coming in, wait, I need the mass of the stick. Mass of the stick, that's 2.0 kilograms. And the radius of our turn, this radius, R, is equal to L. Okay, so R equals L. The box is going to come in, and it's going to hit exactly right there, totally perpendicular. Okay, so it's coming in from this angle, and it's going to hit right there. The center of mass is going to be at the very end of the stick. All right, these little things come up because I put my hand on the pad because I can't help it. I can get rid, can I do something like this? Okay, so okay, so what is that mass coming in? Let's call it mass 1. So mass, yeah, that's not working. Well, I'll just erase those things as they pop up, whatever. So M1, that mass 1 is equal to 0.05 kilograms. And then our V initial for 1, as it's flying in to hit this thing, it's flying in at V10. Okay, so there's no connection. It happens to just have a velocity, and it's going to come in and it's going to stick to the stick. All right, they're going to glom onto each other. What does that mean? That means it's a inelastic collision. Okay, and it's coming in hot, 30 meters per second. So that's pretty much all the stuff that we need. Now, I could ask you to pause and tell me what is the omega final after the collision. So now do you see why I did this? Because basically we have stuck one thing onto another thing, and we have to figure out what their total moment of inertia is. Okay, so that's why we did that. And we're gonna keep calm and carry on. Is there an external torque? You got to ask yourself, is there a torque net? Or does it equal 0? Because if it equals 0, then we can do our conservation of angular momentum. I think it equals 0. We don't have anybody putting torque or forces or any other stuff on this. We're looking from the top down on a table, and everything's got no friction, so we can really genuinely say that our angular momentum initially is equal to our angular momentum finally. That's cons of momentum, angular momentum. Okay, so now we have to figure out a few things. But before we do, I want you to imagine the situation. I'm going to erase this, and I'm going to erase this. Imagine the situation. The box is about to hit the stick. Just about to hit the stick. All right? It's going to hit the stick in a nanosecond, in just the smallest fraction of time. Right before it hits the stick, we've got our L naught. Okay? Just before it hits the stick. This is very important. Why? Because our L naught is equal to I naught times omega naught. Okay? Very important. So I'll put R equals L on this side. Okay? So it's right before it happens, and all we have to do is figure out what the I naught is. Well, we don't have, the only thing moving is the box, right? This mass 1 coming in. All right, that's the only thing moving. So all we need to do is figure out the I for that box. Okay, good. So I for the box. And we're going to easily get our omega for the box pretty quickly. The stick is just sitting there, not part of the initial moment of inertia, or angular momentum. So it's doing nothing. So what do you want to do first? Should we figure out the omega b? All right, well, right before it hits, it's at R. So R omega b is equal to V10, right? That's going to lead us to, did I say what L was equal to? Yeah, 1.20 meters. Okay, so that means that omega b is equal to V10 over L stick. Do we want to keep it as a number, or I'll keep it. I'm going to keep it this way. I don't want to plug numbers in yet. Okay, so we've got the omega b. Okay, these are tough questions because you're like, oh, but is that right? Yes. All right, it's right before it hits, and we're going to do right before it hits and then right after it hits. Okay, that's the only time we really should do our conservation of angular momentum, right before and right after. So right before, that's what we've got, and let's do our IB. So of the box, our moment of inertia, we're thinking of the box just like we thought of the hammer before. It's just the mass of the box times the radius squared. But we've already said that the radius squared is L squared, LS squared. So mass box LS squared. So in the end, let's put all these things together and get ourselves a L naught. It's the mass of the box times the length of the stick squared times our V10 over the length of the stick. I'm going to simplify, get rid of one of the lengths of the stick. So we've got the mass of the box times the length of the stick times our initial velocity. All right. We're going to take this to the bank later and use it. What about L final? Let's find out what L final is. El final. L final is equal to our final moment of inertia times our final angular velocity. Pretty easy. Okay, now all we have to do is figure out what L final is equal to. Where do I have it? Where do I have it? Okay, I think I better draw a more close-up picture. I think I better draw a closer-up picture because we need to see this. All right. First of all, our stick is very thin. And it doesn't have this thing hanging off the end. Okay. Very thin stick. It's got a pivot point here. It's got a box hitting it right here. And the box's center of mass is exactly there. Now it's so thin that this distance to the pivot point is the same, L dotted, is the same as L stick, okay? They're essentially the same. So that's why we just did what we did, okay, first of all. Secondly, we are now attached. We're attached right there. So I can just do a point mass and get rid of all this other stuff. Can I do it? And we're going to call it a point mass right there. Okay, so that's our mass of the box right there. And we've got our mass of the stick, which I hope we know. Did I write that? Do we know? Yep. Okay. So we've got the mass of the box, we've got the mass of the stick, and we need to figure out our final, I final. So we can do our I stick. Well, what is the I stick? It is a, so much for doing it in 20 minutes. This is going to be a long one, so grab yourself some tea. You can hit pause and come back. So I'm just going to carry through. I'm going to do all of it, so however long it takes. I'm going to have to add, so we've got the eye of the stick. I have to add the eye for the box to it, okay? Just like we did the mass hammer, all right? We're going to add that to it. But the hammer was a little bit longer, right, than the stick. The mass of the hammer stuck out a little bit. This time it doesn't, so that's convenient. In fact, I'm just going to write it. The box, mass box, times the length of the stick squared. Okay, so that's one knocked out. We don't need to worry about it. That looks terrible. Let's put a little S on there. So, fine, now all we have to do is the eye of the stick. Well, that's just a narrow rod. Go to your figure 10.12 or 10.11 or whatever it is, and you're going to find 1/3 mass of the stick times the length of the stick squared. So now we can say that our final moment of inertia is 1/3 mass of the stick ls squared plus the mass of the box times ls squared. I think all that makes sense. Hopefully you guys, that all made sense. Now, how do we rewrite that in a nice way? We factor out the L stick, right? So, and we can just call it L. So we've got L squared times, did I say 1/2? I said 1/3 and wrote 1/2. We want M of the stick divided by 3 plus MB. Yeah, good. So that's our final moment of inertia. All of those things are numbers, right? So that gives us a number. So now we can go back in. Let's bring it down a little bit, bringing it down. Let's go back in and solve for omega final, okay? So LF equals L naught, L0, L initial. So I have I final, L squared MS over 3 MB plus MB times omega final. And that equals our initial, which is all these things. MB, I'm putting this here. MB LS V10. And I'm going to solve this equation for this guy right here. All that other stuff was given. So now I can do that. Omega final is equal to my mass of the block times the length of the stick times V10. And I'm going to divide out by the length of the stick squared. Mass of the stick over 3 plus mass of the block or box or whatever it is. Okay, we can get rid of this and one of those. So that's doable. And we can rewrite like this. And we've got our L of the stick, mass of stick over 3 plus mass block, and that is our omega final. Now, what do? We go through and we plug in all the numbers, right? Yeah, my algebra worked out. At least it worked out twice, I think. On my notes, and this algebra was the same, so good. I'm not going to plug in all that stuff and do the units. You guys can worry about the units if you really are wanting to make sure they work out. They do. And we end up with radians per second, 1.74 radians per second. All right, part B. What is the kinetic energy initially and what is the kinetic energy finally? So we're going to look for KE initial and KE final. All right. What was KE? Rotational KE. You know what? here's the good part. Initially, we can do linear, right? We can say 1/2 m of the box times our V1 initial squared. That's our energy. No matter what happens, that's how much energy we have. And so if you don't mind, I'm going to use that initially. But finally, we have to do that one as well. Okay, so we're going to do that in a second. But let's find out what KE 0 is. 1/2 MB V naught squared. That should give you, you can pause it, see if you get 22.5 joules. Okay, so good, there's one. Now we need the final. KE final. Let's do that. It's rotational, okay, first of all. So what does that mean? That means it's 1/2 I omega final squared. And it's the final I too, by the way. So it's not the initial moment of inertia, it's the final moment of inertia. So you kind of have to be careful with that as well, right? So, did we ever find out what that was? You can do this right here. You can come over here and get your I final pretty easy. If you didn't do that already, that's fine. You didn't have to, but you can. You can come up and do that. It ends up being 1.032 kilograms meters squared. Okay, so that's fine. Getting that right here between those two. What else do we need? Oh, we already know omega final. So I'm gonna put in. Let's put it all together. We've got 1/2. We've got 1.032, and we're gonna square 1.74. And that equals a number, and it is 1.57 to 3 orders of magnitude joules. Okay. Everybody's like, oh, we did not conserve kinetic energy. But no, of course we did not conserve kinetic energy. And why didn't we conserve kinetic energy? Hopefully some of you are saying, oh, because it was a non-elastic collision. So non-elastic means that energy was given away in the deformation of one of the objects. So the box stuck to the stick. And when that happens, there's either Velcro there or there's something that is absorbing the energy, okay? And when it's non-elastic, delta KE does not equal 0. Delta KE only equals 0 in an elastic, perfectly elastic situation. So deformation of the car when it hits the tree, deformation of the Velcro when these two things stick together, or maybe it was putty or something that gloms on. There's deformation, deforming of the material or the thing, and that is what takes up your energy in the system. Alrighty. Part C. Let's do part C. Part C. What is the total linear momentum before and after the collision? Total linear momentum before and after the collision. Okay. Well, initially, again, easy stuff, right? Because P naught is our mass of the box times the velocity going in, right? Cake. That is equal to 0.05 times 30. Let's just say equal sign here, and 1.5 kilogram meters per second. Good. Simple, simple. The final, not quite as easy. All right, so let's, again, we're going to move in and zoom in on this situation. So here's our stick. Very thin stick. We've got a center of mass of the stick. We've got a pivot point for this whole scene. We've got some blob coming in. This is initially, it's got V10, and it's coming in and it's going to stick right there on the edge. Okay? Now, our center of mass for this object, this whole thing has some length, but it's uniform. This stick is a uniform stick. That means its center of mass has to be L over 2. All right? So we've got this guy. I'm going to color him blue. We've got this guy blue sticking to the stick. We've got the stick itself, but we're going to consider the center of mass of the stick, the entire center of mass of the stick. All right? So our P final is equal to our mass of the thing times its velocity finally after it sticks. So after the energy is gone from its initial entry into the situation, it was flying in and lost energy to the situation. But we're also going to add in the mass of the stick times the velocity of the center of mass of the stick. It's final velocity. All right, so all we have to do is figure out a couple of things. For instance, VBF, the velocity finally. Well, the length times omega finally. That's straightforward, right? And we can do that. We know what omega final was. So our length is 1.2 meters. We're going to multiply that by 1.74, and we're going to end up with radians per second. We're going to end up with our 2.1 meters per second goes to radians, goes away. So we can put that in there. We know the mass of the blob or block or whatever it is. We know that. We know the mass of the stick. So our next thing is to figure out what VCMF is. Well, that's L over 2. That's the radius from the pivot point, L over 2, from there to there. And times our omega final. And it's seriously that easy. which essentially is 1/2 VBF. So we can divide that VBF by 2, and we end up with 1.05 meters per second. Now, you can make it easier on yourself if you want to, mathematically, and you can note that if you throw all those things together and do some algebra, you might want to play around with it. Why don't you? I would, if I was me. You actually end up with the mass of the stick over 2. This is the equation you get. If you add all those things in together, this and just put the algebraic symbols in, you'll get this. That makes it really nice because you can then plug in less numbers into your calculator. It takes less time. That's the bottom line. You plug those numbers in and you end up with 2.19 kilogram meters per second. Okay. So, was linear momentum? Let's think about this for a second. Was linear momentum conserved? Well, this does not equal 1.5 kilogram meters per second. Okay? So we are not conserving linear momentum. Something happened, but that was not conserved. Okay? But we did conserve angular momentum. All right, angular momentum is a a little bit deeper conservation law. So good. We are now done with 10.6. So chapter 10, we're not doing, I'll just put it on here. Chapter 10 runs up to 10.6. So that means that there's no 10.7. All right, we're not doing it. So don't worry about 10.7. And next week, now that you got your videos, you can do all the homeworks and you can do all the stuff, and it should make things easy. And yeah, we're going to be doing a lot of labs next week. So there's all the lectures. Okay. Good night.